Jai Hind to all of you. I am Dr. Ritish Kumar, Assistant Professor in Department of Electronics and Communication Engineering at Ajay Kumar Garg Engineering College, Ghaziabad. So, in this lecture, we will discuss the topic of measurement. We will include the topic of VSWR and dielectric constant here. VSWR is a voltage standing wave ratio, which is important property of a device or microwave device such as waveguide and transmission line as well. And dielectric constants is a property of the material that we have used in the designing point of view of a microwave device such as amplifier, filter, and antenna as well. So let's begin the lecture. Measurement of low VSWR, right? Measurement of low VSWR, you have to focus here. So, first before starting the topic, we need to understand what is the VSWR. So, VSWR is the voltage standing wave ratio, right? So, VSWR is directly related to the reflection coefficient. It always occur in the case of whenever we get the mismatch between the load impedance and the characteristic impedance of a transmission line such as waveguide. If we talk about the waveguide, right? So, if the waveguide obviously by default the characteristic impedance of the waveguide is represented by the Z naught. If we take the load impedance of the waveguide is ZL, in that case we have a reflection coefficient is equal to ZL minus Z naught divided by ZL plus Z naught. Here you can observe here, whenever we have a large difference between reflection between load impedance and characteristic impedance of the transmission line or waveguide, then we have a large value of reflection. If we have a large value of reflection, then we finally we have a large value of VSWR. Why? Because VSWR is the 1 plus reflection coefficient and 1 minus divided by 1 minus reflection coefficient. So, if the reflection coefficient value becomes large, then we will have a large value of VSWR here. So, in the mismatching condition, always we have a VSWR pattern within the waveguide. So, if we talk about the matched condition, so in the matched condition, ZL always be equal to Z naught. So, in that case there is no reflection, that means the reflection coefficient would always be equal to 0. If the reflection coefficient is 0, then then we do not have any kind of standing wave pattern. So, in that case the value of VSWR always be equal to 1. So, we can say the range of the VSWR lie in between 0 to infinity. Sorry, this should be 1 to infinity, right? Now, that is the before starting to measure the VSWR, that we need to understand the what is VSWR. So, I hope this is clear to all of you what is the VSWR, how we get the VSWR in the transmission line of waveguide. So, here you can see the measurement setup here. So, in the measurement setup we mentioned the microwave source, pad, slotted line, load, crystal detector and DC voltmeter here. So, main thing is here the slotted line section. What is the slotted line section? Here we mention the diagram of slotted waveguide section. So, this is the slotted waveguide, right? This is the waveguide. This is the slot, and this slot is non-radiating slot. This is a knob. So this knob is a movable knob. You can move it from left to right, whatever the direction you want to move, you can move it over the slotted over the slotted section. And you can see this one is the scale. From this scale you can measure the distance with respect to the reference point. So this is about the slotted waveguide section that we have used in this microwave test when set up. Now how it works. So as we know, if the load impedance is different from the characteristic impedance, always we have a VSWR, and that VSWR we need to measure by the microwave component such as slotted waveguide section. So whenever you move this knob from left to right, we will get a pattern. That pattern is known as VSWR pattern, and that pattern we have mentioned over here. And you can see we have B minimum, B maximum, B minimum, B maximum, B minimum, B maximum, B minimum. So this is a repeatable this is a periodic form of the pattern, we can say, and this pattern is drawn over here, and here the x-axis represent the distance and y-axis is representing the voltage magnitude of the voltage of the signal. So here why we mention the lambda zy2 here, because the distance between two minima always with the lambda zy2. And why we take the lambda z, because we are dealing the experiment from the waveguide, because waveguide is a guided media, that's why we have to take the guided wavelength here. Now as we know the standing wave pattern, in this case we have the two values, B maximum and B minimum. So we can measure this value directly with the help of the probe. So we can also call this is a probe method. So by using this probe we can directly measure this B maximum and B minimum by using probe and the measuring device such as CRO or DSO or DC multivoltmeter as well. So we have the value of B max and B min. If you take the ratio of these two, B will get some value, and that value is known as VSWR, because in other terminology, in other way we can say VSWR is the ratio of maximum voltage to the minimum voltage. So this is about the how to measure the low VSWR by using the slotted waveguide, and the measurement setup we have mentioned over here. So I think this is clear to all of you how to measure the low VSWR, very simple technique to measure it. Now the next one is the measurement of high VSWR, and the method of using to measure the high VSWR is known as double minima method. Why we call the double minima method here? Because we are dealing with the two minima in the pattern, first minima and second minima, right? If we consider two maxima in the pattern, then we call double maxima method as well, because the distance between the two maxima and two minima would always be equal to the same, that is lambda z by 2. And why we take the lambda z here? Because we are dealing with the guided media, and this lambda z is known as guided wavelength, right? So now I am considering here the two minima, and the distance corresponding these two minima, the first distance we can say D01 and D02. So as we know the distance or separation between two minima always be equal to lambda z by 2. So we can write lambda z by 2 d naught 1 minus d naught 2, and lambda z is equal to 2 times of d naught 1 minus d naught 2, right. So this is a guided wavelength that we can calculate by using the separation of these two minima. That now what is the d1 and d2 here, right, that we will discuss a few time later. Now here if we consider two maxima, now I am considering now the two minima. Now if I consider the two maxima, then what will happen? In that case, the lambda z, again the distance between two maxima would always be equal to lambda z by 2. So lambda z by 2 again d naught 1 minus d naught 2. If we consider the separation between one minima and one maxima, then it would always be equal to lambda z by 4. Then in that case we have to take the 4 times of the separation between b minima and b maxima. That is the basic concept of considering the minima, maxima and minima. So here we are dealing with the two minima point, that's why we call the double minima method. Now what is d1 and d2 here? So d1 d2 is the point where the value of voltage under 2 times of minimum voltage. So this point is also known as doubling power point, and this these 2 point is known as doubling power point, and corresponding to this point, first point we have a distance d1, and corresponding to second point we have a distance d2. So so we know the separation of these 2 points where the doubling of the power is achieved. So why we take these 2 points, we will understand or we will get to know in the next slide. So here you can see for the T10 mode, the cutoff wavelength is always be 2a or 2 alpha, we can say, and guided wavelength is lambda naught under root divided by square root of 1 minus lambda naught divided by lambda c whole square. But this is the an empirical formula of VSWR. So d1 d2 we know by looking this graph. This is nothing but a zoom version of it, right. We know the lambda z, that is guided wavelength, that is the separation of, with the help of this separation, two minima separation, by putting the value of lambda z and separation of this doubling power point, then we finally we will get the VSWR of the system, right. So this is the method of measuring high VSWR by using double minima method. I hope this article is clear to all of you. Next, measurement of dielectric constant. So dielectric constant. So if we talk about the material, so material can be characterized by looking the properties such as conductivity, permeability and permittivity. So permittivity is nothing but a dielectric constant of the material. That is the important property of the material that we need to understand how we can measure the dielectric constant, because by using this we can understand what kind of dielectric constant we can use for the designing of the antenna, filter, amplifier, that is the microwave components, microwave devices. So this is an important one, I can say. So we already know what is the permittivity. Permittivity is the epsilon naught and epsilon r. We all know the equation of it, where epsilon r is the relative permittivity and epsilon naught is the permittivity of the free space or permittivity of the air as well. So every microwave material has the relative permittivity is given by this equation, right? This is a complex permittivity. So always microwave materials or materials has the permittivity in the complex form. This is the real part of the relative permittivity and this is the imaginary part of the permittivity, right? So and here you can see the tan delta, right? So tan delta is the loss tangent. This one is the loss tangent, as we already read in the subject of electromagnetics, EMFT, that is called electromagnetic field theory. So this is a loss tangent. So we can define loss tangent is the ratio of the complex quantity of the relative permittivity to the real value of the relative permittivity. And we can see loss tangent gives an idea. What is the loss tangent? Loss tangent gives an idea of how lossy the medium is. That is, it is a measure of energy lost in the form of heat when a wave is propagated through the medium. That is already we read in the subject of electromagnetic field theory. So if we are able to measure the dielectric constant of the material, then we also measure the we also calculate the loss tangent of the material, because both are related to with each other. If we are able to know one parameter, we can able to find the other parameter as well. So here in the next slide I will discuss one well known method or to measure the dielectric constant, that is cavity perturbation method. This is a very important method here. What is the cavity perturbation? This is one of the research article, cavity perturbation method. So why researchers are doing most of the research to get or to understand the properties of the material by using cavity perturbation method. So why we call cavity perturbation method? This is a cavity, you can see here, waveguide cavity, right? This is a cavity. Now this is a coupling hole, also we can say iris. This cavity hole is known as iris. Now this is you can see here we have attached a BNA to S parameter test set and BNA, again to set S parameter set and BNA, right? What is the VNA? VNA is the vector network analyzer. With the help of vector network analyzer, we can able to measure scattering parameters such as S11, S12, S21 and S22 of a microwave component. So these scattering parameter help to get the characteristics of the material. Now how it helps, then we will discuss here. So here you can see because BNA has a different kind of port, that port is known as SMA port, and here we are using the waveguide. So the cable that comes from the VNA, that is vector network analyzer, that is coaxial cable. So we at the input side and output side we have to attach, or we need a kind of converter. Means coax to waveguide port converter we need to attach at the input port and output port as well. So, this is a coaxial to waveguide converter, this is another one coaxial to waveguide converter. Now, here you can see here this is a non-radiating slot as we have in the case of slotted waveguide section that we had discussed in the previous measurement technique of VSWR. So, this is a non-radiating slot and this is a sample that we need to this is a sample that we want to know the dielectric constant of it. So, think how to measure the dielectric constant with the help of this cavity. Cavity itself is cavity itself has its resonating frequency. So, suppose if we don't have any kind of sample within this cavity, then we have a S21 because S21 is a transmission coefficient we can say, or in terms of power transmission we can say. So, when there is no sample, the power flow from port 1 to port 2 and that power we can we can find with the help of scattering parameter of S21. So, without using any sample we have a S21 like in this way. Suppose this is an empty cavity. So, cavity itself is has its resonating frequency that is represented by this one. This is a frequency and this one is the magnitude of S21. So, this is a transmission of power from 1 to 2 and its resonating frequency is given by this equation. Suppose this is an empty cavity. When suppose if you want to know the dielectric constant of any material, then you need to disturb the power that is flow from port 1 to port 2. Means perturbation means you are disturbing the something. Whenever you are disturbing something, then you will get a different kind of power, or you can receive different kind of power at port number 2 by using the sample. So, by using the sample you are perturbing something inside the cavity, then the power flow is disturbed from port 1 to port 2. Because of it you will have the frequency shifting from empty cavity to the sample number of 1, right. Previously in the empty case the frequency comes to at this point, suppose F1, and after using the sample the frequency shifted towards the lower side and it gives the value suppose F2. So, you are able to get you are able to know the separation of these two resonating frequency. So, first one is the without using the sample and second one is the using sample. Suppose if you want to measure the another one sample in place of the first one, then you will have the frequency shifting like F3, right. So, the question arises why the frequency shifted to the lower side, because because without using the sample the media inside the cavity is vacuum or and air. So, in that case the dielectric constant always be equal to F epsilon R equal to 1. But when you are inserting something inserting material inside the cavity and this material has its own dielectric constant, suppose on dielectric constant, and that would always be greater than 1. So, as we know the frequency is inversely proportional to the square root of f under root square root of epsilon r. If you increase the epsilon r, then frequency shifted to the lower side. If you decrease the epsilon r, the frequency shifted to the higher side. That is the relation between relative dielectric constant of the and frequency, resonating frequency. That's why because sample has a dielectric constant more than the air, that's why the frequency shifted towards the lower side. Now by using this separation f0 and f1, so by putting this separation in this equation, so what is the Vc and Vs? Vc is, and here V is the volume, and C is Vc is the volume of empty cavity, and Vs is the volume of sample filled cavity, right? So by putting these all the values in the equation, f0 we can get from this empty cavity, and f0 minus f1, that is the difference or shifted of the resonating frequency that we can get from this by using the VNA. So by putting these all the values, we finally we will get the real value of relative permittivity. At last, the complex permittivity, that is because we have a complex permittivity and it has its um, uh, uh, imaginary part of the relative permittivity we can get by using this formula. Here we need to put the value of quality factor of the empty cavity and the sample filled cavity here. So these value we can directly read with the help of VNA. VNA is the vector network analyzer. So by using this VNA we can directly read the value of quality factor. So by putting all these value we get the value of real value of it, real value of relative permittivity and imaginary value of permittivity. So at last we are able to understand, or we are able to calculate the value of relative permittivity of the material. So I think this cavity perturbation method uh, you can understand. So I hope these two topics, the first one is the measurement of VSWR and the measurement of dielectric constant by using cavity perturbation method is clear to all of you. Thank you everyone.